Okay, let's do problem 6.16 on page 185. So this problem, we're looking at a cyclist going around a curve. Okay, so we know that we have a 20 meter radius curve. We also know that the speed is 12 meters per second. And we want to know the minimum, the least possible coefficient of static friction between the bike tires and the ground. Okay, so first of all, does it make sense that if we want to maintain a curved path, we need to have an acceleration to change our velocity? And that acceleration is going to be pointing toward the center of the curve. Okay, well, in this situation, let's draw a force diagram now, and let's look at what it is. Let's think about what force is actually keeping the bike from flying out of the curve. So imagine you're riding your bike and you're going around a curve on the road, and let's say you're taking the turn pretty fast because, you know, why wouldn't you? But let's suppose that you want to take this turn fast, and perhaps there's a lot of gravel on the road, or maybe it's icy, or some reason why it's slippery. So if you hit a slippery spot, you're not going to go in a curved path anymore. You're going to go off the road. You're going to essentially just go in a straight line path. So instead of making a curved path, you're going to then just kind of veer off and go off just in a straight line wherever it is that you hit the slippery spot. But in order to prevent us from slipping, we need to have something pulling us in toward the curve. And in this case, it's going to be friction. So we're going to have a friction force that is in toward the center of the curve. Now, sometimes it's helpful to draw that diagram from another vantage point. So I'm going to tilt this picture so that instead of looking at it from above, let's look at it from the back of the bike. Okay, so if we're looking at the back of the bike, okay, so just pretend that's the back of the bike. Let's draw the forces here. Okay, so let's say that the center of the curve is over here, so that in this situation, the bike is moving away from us. So let's say that the bike, we're looking at the back of the bike, and the bike is driving into the page, into the screen. Okay. So we know that we have the friction force this way, keeping us in the curve. Oh, by the way, is that going to be a static or kinetic friction force? Well, in this case, it's going to be static because we're hoping that the tires of the bike do not slip left and right. They're going to be rolling forward, yes, but we don't want them to slide to the left or slide to the right as we're moving around this curve. So we want to have no skidding. We don't want the tires to slip. We don't want them to skid. So that means that we have to have a friction force that is static so that there's no slipping, and we only have rolling and no slipping. Okay, let's draw the other forces. We know that we've got weight acting downward, and of course, don't forget about the normal force acting upward. Okay, so here's our force diagram. Now, let's think about what's the next step that we do in our diagram, or after we make our diagram. Well, now we're going to apply Newton's second law, just like we did with the previous chapter. We're still applying Newton's second law. The only difference is now we have some circular motion, and the circular motion just means that instead of regular F equals ma, we're going to have F equals mv squared over r. That's the only difference. Okay, so now let's look at our centripetal direction. And the centripetal axis, the centripetal forces here, that is looking at the axis that acts along the radius of the circle. It is not going to involve our y-axis with the normal force and the weight. That is just going to be regular F equals ma, just like before. Okay, so let's also look at this sign convention for the centripetal axis. And because it doesn't really make sense to say left, right, up, and down, it makes more sense to say whether something is pointing in toward the center of the curve or whether it's pointing out away from the center of the curve. So if you have forces that are pointing inward, those are considered to be positive, whereas forces pointing outward are going to be negative forces. All right, so let's look at our force diagram, and we're only looking at the forces along the horizontal axis, that is our centripetal axis. Okay, so here we've got just one force, and that's the friction force. So the static friction force, is it going to be positive or negative? Well, this case is going to be positive because it's pointing inward and not outward. All right, so we're going to put our friction force there. It's the only one. Whoops, what happened? Whoop. Okay. And that equals mv squared over r. And this v in this expression that's the speed, that's the 12 meters per second. Okay, so now let's make some substitutions here. We are trying to figure out the minimum coefficient of friction, not the minimum friction force, which is what we have right here. So let's substitute, and instead of the friction force, let's substitute mu times n for that. Okay. All right. Well, we see that we have the normal force in there, and that kind of signals to me that it's time to go to the y direction. So let's do the sum of the forces in the y direction. Okay. Well, I know that I've got my normal force up, and I've got my weight force down, and I know that there's a constant zero velocity in the vertical direction, so I don't have any acceleration. Okay, so then this tells me that the normal force is equal to the weight. And then I can make a substitution for weight and call that mg. And now we can put that in over here. And we're trying to find this value of mu. Okay, so actually I'm going to solve this equation for mu first. Whoops. Let's solve this for mu s. Okay, so mu s is going to be all of this, and then divide by the normal force. Okay. So now let's see. Let's plug in for the normal force. Okay, so the normal force is m times g. Well, looky there. The masses cancel. That means that it doesn't matter what mass this bike is, or in fact, whether it's a car or some other heavier object, maintaining this curve, it only depends on the speed and the minimum coefficient of friction only depends on what speed you want to take it and the radius of the curve, as you see there. Isn't that sweet? Okay, so let's write our givens over here. Okay. Oh, actually, we already wrote the givens up there. I'm going to write them down here again anyway. Okay, so we've got v is 12 meters per second. We want to know what is that mu, and we know that the radius is 20 meters. Okay. So now let's plug and chug and see what we get. Okay, square that. Then we have 20 meters and 9.8 meters per second squared. Okay, so let's run the calculator and see what we get there. Okay. All right, so 0.73 to 2 sig figs is the minimum coefficient of static friction that's required to keep this bike going in a curved path. Let's just look and see what we did in this problem. Okay, so we had a circular path and we had to apply Newton's second law, but this time we're looking at the centripetal axis. So we're applying Newton's second law as mv squared over r. And then we put in our forces, applied Newton's second law. We also went over to the y direction, got our normal force. And then again, we're just solving a system of 2 equations and 2 unknowns so that we can solve for the target variable.